All right, so welcome back. Before we get started, a little bit of administrative note. So first of all, your midterm exam will take place next Friday. So we still have several lectures there. I am only 3 lectures behind, so I currently don't know what the coverage will be. I will post a announcement like what to know for midterm 2 on Friday. So this Friday we'll go over what to expect on your second midterm. I'll also likewise post a survey on Bring Learn just to ask your opinion in what I should be covering in our buffer lecture on next Wednesday. So right now, what I can tell you is midterm 2 will cover whatever after the first midterm, which is I think we end on the physical meaning of entropy and link entropy with probability to whatever we finished on our next Monday's lecture. And I'll have more information on Friday. And what else? Right. Yeah, and we're back in person, so hopefully we'll remain back in person for as long as we can. For today's lecture, I'll likewise post our recording on our YouTube channel. So the Zoom recordings are still on BrainLearn. It's a little bit inconvenient to have the recordings in 2 different places. I'm trying to fix it, but you'll see today's lecture recording on YouTube channel. All right, any other questions before we move on? Nope, we're happy? Okay, sounds good. So let's get started on our today's lecture. So far in our previous examples, we went over the derivation of the Gibbs equations from the 6 fundamental equations or the definition of our state functions. We generated the set of Gibbs equations that's talking about closed system, PV work only, thermal, mechanical, and material equilibrium or thermodynamic equilibrium. Right, so just to refresh your memory, when we're saying these Gibbs equations are derived for reversible processes only, the bottom line is we're trying to use the Q reversible equals to TdS, and then the work reversible equals to negative PdV, right? And my du equals to dq plus dw according to our first law of thermodynamics. So just to refresh your memory a little bit in what we did in our last lecture. Now in our last week's lecture, we also went over the use of Gibbs equation to link the partial derivatives to certain state functions, and also to derive Maxwell relationships using the Euler's reciprocity relations. And then the derivation of, say, volume dependence of internal energy or pressure dependence of enthalpy. And in our last lecture, we went over how to use those derived terms to solve for change of state functions. All right, so today, we'll just do one more thing. We'll take one step further to remove the material equilibrium. So instead of saying material equilibrium, we're putting material equilibrium to be a question mark, right? And what we want to do today is first to introduce a term called chemical potential that gives us a way to describe material equilibrium. And then we'll discuss, after defining the chemical potential, then we'll discuss what is the sign of chemical potential at equilibrium and prior to equilibrium. And at the end, we'll talk about what is the physical meaning of chemical potential. All right. So that's our ultimate goal, trying to describe material equilibrium. So getting started, right, like what we said, now we want to similarly discuss the Gibbs equation. Just to keep our life simple, let's consider a one-phase system. One phase meaning it's either all solid, all liquid, or all gas, right? Only one phase. And you have different chemicals or different substances that are in thermal and mechanical equilibrium. So thermal and mechanical equilibrium just tells us my temperature and pressure are well defined. right? So my temperature and pressure, it may not be, it's not zero, right? But it has a well-defined number. But the system itself is not at material equilibrium, right? So there can be different things going on, might be a chemical reaction going on, right? So from reactant to product. So what is our change to our Gibbs equation? So thinking about our Gibbs free energy, we can write our Gibbs free energy as a function of different variables. So it's obviously a function of temperature and pressure. At the same time, it will also be a function of the number of moles of your different substrates. Right, so in here, N1, N2, N3, all the way to Nk are all the chemical species or chemical substances involved in this reaction equilibrium or material equilibrium. Right, so we have K different substances involved in the in the material equilibrium. Right, and then what we know? We also know that we can write the total differential, right? So for a function dz as a function of x and y, you should know how to write the total differential. It equals to the partial derivative of z over x at constant y dx plus partial derivative of z over y at constant x dy. Right. So if we do the same and write the total differential of my Gibbs free energy, now we have multiple variables. What does it look like? So my dg, now it's a function of all t, p, n1, n2, n3, all the way to nk. That equals to partial differential of Gibbs free energy over pressure at constant T and Ni. So this Ni here just tells you that the number of mole of all my substances are kept constant, 1, 2, 3, 4, all the way to K. Right? So I is basically a list of number ranging from 1 to K. dP plus partial derivative of G over T at constant P and Ni dt, and well, it's everything else is just a sum of the change of number of mole of each substances. So the way we write it is just the sum of I equals to 1 all the way to K and partial derivative of G over number of mole of species I at constant T, P, and number of moles of other substances times dNi. All right, so in here, I just want to quickly highlight one thing. Like, what is my I and what is my J, right? So imagine a reaction. We have A plus B goes to C plus D. Right, so in my I, we have A, B, C, D. Right, so the total term in here will be the partial derivative of G, dG over dNA, while keeping constant T, P, number of mole of B, number of mole of C, number of mole of D, constant. That's this one. And plus dG over dNB, while keeping T, P, NA, NC, ND constant. Right, and obviously we have the term for C and D. All right, so this is just the written out version of that sum over there. And done. All right, so what are these partial derivatives? The first thing we can use is let's look at the first two terms. So in these two first terms, my total number of species or substances, Ni, are always kept constant. All right, so in these two partial derivatives, my Ni are always kept constant. So that relates back into the derivation we did in our previous cases, that we can write the partial differential of G over T at constant pressure and constant Ni to be equal to negative S. Likewise, dG over dP at constant temperature and Ni equals to V. That's the one we derived in our previous lecture. All right, and the reason we can do it is by writing out the total differential, we know that Ni is constant in these two terms in front. So we can simplify our expression here using this relationship to rewrite my dG, or the infinitesimal change of Gibbs free energy of a system that's not at a material equilibrium, equals to negative S dt plus V dP. And plus this entire thing, we have I equals to 1, the sum of the term from I equals to 1 to I equals to k, partial differential of G over Ni at constant T, P, and for all other N that's kept constant, times dNi. All right. So whatever we're doing here is simply calculus. We recognize the fact that the Gibbs free energy is a function of temperature and pressure, and also the change of the number of moles of different substances involved in a material equilibrium. We write out the total differential of my Gibbs free energy, and using the thermodynamic relation, simplified it to find out, okay, so the differential of the system that's not at material equilibrium is negative S dt plus V dP. That's the same as what we see before, now with this term at the end. So from here, we're just using calculus, we're just using this mathematical operation, and then we define chemical potential. So the chemical potential, which is mu I, it's, well, so here, I, the subscription I just tells us, hey, that's the chemical potential of my substance I, right? So that I can be my A, B, C, and D. So the chemical potential mu I of substance I in a one-phase system is defined to be the partial differential of Gibbs free energy over the change of your number of mole of that substance I at constant T and P, while other number of moles of other substrates are kept constant. For one phase system, now we're not talking about different phases right now. All right. Or the other way to put it is back to our Gibbs equation. What we have found out is, in addition to this original form, we're adding this chemical potential term into our Gibbs equation for the dG. That's our derivation. All right. So with that in hand, obviously we can do the same for the rest of the Gibbs equation, right? Just using the terms of thermodynamics and using the definition of the thermodynamics. So for example, if we look at my delta H here, right? So my delta H, or H is by definition equals to G plus Ts, or the same as say like Gibbs free energy is by definition equals to H minus Ts. These two are the same. Now we can write dH to be equals to dG plus dTs, and my dG is given here. That's the negative S dt plus VdP plus the sum of my chemical potential times the Ni plus TdS plus SdT. Right, so my SdT cancel out. My dH equals to TdS plus VdP plus my chemical potential. All right, so you can do the same for the rest of the Gibbs equation. So now talking about material equilibrium, we have this chemical potential term that we add at the end. And I just want to put the definition of my chemical potential on here. That my chemical potential of my substance I is defined as a partial differential of my Gibbs free energy over the Ni at constant P, and Nj not equal to I for one phase. So this is the first part of our today's lecture. We started from the fundamental Gibbs equation. We then removed the idea of not having material equilibrium. So my G is a function of not only temperature and pressure, but also the change of number of moles of all my chemical species. And then only by writing out the total differential, we got that idea of this sum must be something of interest to our mind, right? So we define our chemical potential to be the partial differential of Gibbs free energy over the change of number of mole of the substance I, right? And this total term is called chemical potential. That's the first part. Now the second part, why do we care about chemical potential, right? So in this part, we will first talk about what is the sign of chemical potential at equilibrium and not at equilibrium. And then we'll specifically look at phase equilibrium of one substance, which is more easy to deal with. And by derivation of chemical potential of different of substances in different phases, will end up to have a physical meaning of chemical potential, right? So the first goal here is to talk about, okay, what is the sign of this term when it's at equilibrium or not at equilibrium? And how do we use that knowledge to solve, like phase equilibrium, to solve something we care about? So getting started, this part, we start by looking at the fundamental property of our Gibbs free energy, right? So Gibbs free energy itself is an extensive state function. So what does it mean by it being an extensive state function? So it basically tells us the total Gibbs free energy of my system equals the sum of each part, right? So if you consider my system now containing, say, water, both in liquid water form and in water vapor form, the Gibbs free energy of my entire system equals the Gibbs free energy of water vapor plus the Gibbs free energy of my liquid water. Or the other way to put it is we can write G, the total Gibbs free energy, equals to the sum of all phases of the system. Now here, alpha denotes the phase of the system. All right. And now using calculus, if we are writing the differential of my total Gibbs free energy, we know that dx plus y equals to dx plus dy. So my total Gibbs free energy, dg, equals to the sum of dg alpha. Right, so we're just taking the sum of every part of my system. Now my different parts may have different phases. Let me actually use black. It's more straightforward. And now let's focus on this term here, right, on this dg alpha. So what is this dg alpha? This is the Gibbs free energy of my substance in phase alpha. Right, so using our equation we just derived, what we have here is effectively saying dg alpha equals to negative S alpha dt plus V alpha dp plus the sum of species I added together. Right, so alpha tells me what are the phases of my species. Now instead of only one species, you can have multiple species. So I denotes for substance I, and alpha denotes for phase of that substance. So imagine we have like water and alcohol mixed together, and we're doing vaporization of that water-alcohol mixture, right? So you eventually will get, say, H2O liquid plus ethanol liquid, and go to H2O gas and ethanol gas. Now in here, my H2O and my ethanol are my I. So inside my I have my H2O and ethanol, right? And inside my alpha, or my phases, we have liquid and gas, right? And in here, like, what does it mean when we're knowing each differential of my Gibbs free energy of phase alpha? What does it do when we put it to the overall dg, right? So what do we have here? So if we're doing the total summation of all phases, there are some of the things we know. For example, in here, what is my S alpha? So that's my entropy of my alpha phase, right? So that's my entropy of my liquid phase. So the sum of my liquid phase and my gas phase entropy equals to the total entropy, because entropy itself is also an extensive function, right? So considering this reaction mixture, you have liquid and you have gas. So the entropy of all the liquid part plus the entropy of all the gas part must equal to the total entropy, right? Entropy itself is extensive state function. So in here, what we have is the sum of my S alpha equals to S. And likewise, the same logic applies to volume, right? So volume of all the liquid part plus the volume of all the gas part must equal to the total volume of my system, given my system only contains liquid and vapor, right? Right, and these are true because volume and entropy are my extensive state functions. So taking together, my original dg thus becomes dg equals to negative sdt plus vdp. Now we have a double summation. We need to sum over all the phases, and we need to sum over all the substances of my mu I alpha dni alpha. All right. Or the other way to put it, in this system, what we have is, if we write out my, my double summation, what are we getting here? We have the double summation of alpha and I of my mu I alpha, the ni alpha, right? So if we consider this system with two substances and two phases, writing it out is simply mu H2O of liquid, the NH2O liquid, plus mu ethanol liquid ethanol liquid, right? And plus mu H2O gas, H2O gas plus mu ethanol gas, ethanol gas. Nothing fancy, right? Just double summation. And what else do we know about material equilibrium? So that goes back to our introduction to delta G, right? So if you remember when we introduced delta G, we have, if we plot G as a function of time at constant T, P, isolated system, right? So it's a downhill diagram. And at equilibrium, we have dg equals to 0 at equilibrium. So back to this equation here, when we're talking about material equilibrium, what are the things we know? We know that dg equals to 0 at equilibrium, or more specifically, at material equilibrium at constant temperature and pressure. What else? We have dt and dp equals to 0 because it's constant temperature and constant pressure. So our conclusion here is our chemical potential that we have just defined must equal to 0 at material equilibrium, closed system, PV work only, thermal and mechanical equilibrium. Or I guess this term itself is equal to 0, but it doesn't tell us what is my chemical potential, right? Remember, my chemical potential is this mu I term. So now we know this double summation equals to 0 at material equilibrium. And just to refresh your memory, we have the chemical potential defined for species I in phase alpha equals to the partial differential of Gibbs free energy in phase alpha over the change of number of mole of that substance I in phase alpha. So let me replace that one phase diagram with a more complete definition. All right, so what we find out in this part is, well, this double summation, or the total sum of my chemical potential times the infinitesimal change of my species I in phase alpha, the total sum of this term goes to 0 at material equilibrium. Right, and we completed our definition of chemical potential for a multi-phase system. So before we move on to look at phase equilibrium, I want to quickly ask you one question. Is my chemical potential intensive or extensive? Raise your hand if you vote for extensive. If you vote for intensive. Okay, so it is intensive. What do we have? Our Gibbs free energy is extensive, right? But we divided by the number of moles in our expression here. So that means my chemical potential is an intensive property. Okay, let me make some space. All right. And now let's move on to look at phase equilibrium. So this is going to be a application in what we know and try to find out an idea, right? We know that this double summation equals to 0 at equilibrium. But what does that tell us for chemical potential of species in a phase equilibrium? So we're going to look at two phase transfer processes. One is at phase equilibrium. The other is not at phase equilibrium. And we'll see how my chemical potential relates to each other in these systems. First one, let's look at a reversible phase change, or like vaporization of water. And let's say this at 1 atm and 100 degrees Celsius. Right, so it's a reversible phase change or reversible vaporization of water. So what do we know? We know that this double summation of my chemical potential times the differential of the number of mole of the substance that's changing must equal to 0 at equilibrium. Right, so this term equals to 0 is the derivation we just did. And if we write out this double summation, we basically got two terms, right? It's just water vaporizing. So we have one substrate, two phases. So in total, we have two terms in my double summation here. With me so far? So let's imagine this one. Let me just draw it out. It might be easier. So we have liquid goes to gas. Right, so in this process, let me define a new term called DnH2O. So it is a positive number that represents number of mole of H2O flowed from liquid to gas. Right, so we define it to be a positive number. And then in our relationship, what do we have here? If we focus on the amount of water flow out from the system, we have the DnH2O equals to, this one, let's say, positive, equals to the negative of DnH2O liquid. Because water is floating, my substance is flowing from liquid to gas, right? So the number of mole of my liquid water is decreasing. So that's where that negative sign comes from. All right. Or the other way, I can put this one equals to the negative on the left. It's the same idea. And also, we have DnH2O equals to the gas of NH2O, right? So these amount of water has been transferred to be gas, right? So the number of my gas phase water is increasing. So that's a positive number. So this one is negative, this one is positive, and these are positive. All right. So now let's plug in this number into our original equation. What do we have? So let's see. This one, my DnLH2O equals to negative DnH2O. My DnGH2O equals to my DnH2O. Right, so what we end up getting is this expression to be mu L H2O, and then there's a negative in front, DnH2O plus mu J H2O times DHN H2O equals to 0. Right, so we can write that same term out. So we can write this same term out. We get it to be mu G H2O minus mu L H2O times dNH2O equals to 0. Right, so far so good. So what we're using here is just a simple concept, right? We know this double summation equals to 0. And in a system where there's only reversible vaporization of water taking place, we only have one substance, two phases. So we write out this double integral and it equals to 0 at equilibrium. Right, and then what we find out is since we only have the liquid water and gas water interacting with each other, the total number of water that's being vaporized is basically the same, right? So whatever goes out from my liquid is whatever my number of water vapor increase. But the sign is flipped. So what we end up getting is an expression here. So in here, we know that dNH2O, this is a positive, not zero number. So that even at equilibrium, my infinitesimal change of my number of mole of my water is not 0. So this one is a non-zero number. So that tells us my first term here, or my chemical potential term, must be equal to each other. Or if we generalize our conclusion, we can write that mu J for any substance J in phase beta equals to mu J in phase delta at phase equilibrium between phases beta and delta. Right, so in this process, let's add some of the previous concept we must have, right? You have like constant TP, you have like closed system, the thermal and mechanical equilibrium. So those are the assumptions you need to keep. But nevertheless, what do we find out is my chemical potential of the substance in two different phases must equal to each other when we have phase equilibrium. With me so far? Okay. Next one. You would imagine now we move out from reversible process, or we move out from phase equilibrium into talking about irreversible processes. So let's think about the same reaction. It's still water vaporization, but now it's happening at 5,000 K. So it's definitely an irreversible process. Once my water vapor once my water liquid got transferred into water gas or water vapor at 5,000 Kelvin, there's no way it's going to come back. Right? So doing the same kind of analysis, can we find out a relationship between chemical potentials of my liquid water and my vapor water in this condition given? Right, so that's our goal here. So what do we know? We have our expression for dG describing chemical equilibrium, material equilibrium. That's our Gibbs equation. And in here, what else do we know? So that goes back to our figure here. So can people see it? All right, okay. So last time we were using dG equals to 0 at equilibrium, right? And we know something else, right? So dG equals to negative SDT plus VDP at equilibrium. That's our Gibbs equation. What about before equilibrium? So if we draw a line here, now before equilibrium, what's the sign for our dG? Negative, right? So my dG is smaller than 0 prior to equilibrium. So writing that down is we have dG smaller than my negative SDT plus VDP. Right, and this is the Gibbs free energy of my at my equilibrium. That's the dG at equilibrium. So what that tells us is this term, double summation, alpha and I, mu I alpha, the Ni alpha must be a negative number. And using the same logic, writing out my double summation, what do we have? We have mu H2O of liquid, which is a chemical potential of liquid water, times the differential of the NH2O liquid. That's the amount of liquid water, the change in the amount of liquid water, plus the chemical potential of water vapor times the differential of H2O of gas phase vapor. And this is smaller than 0, right? So this step is just writing out the double summation. No mysterious. And using the same logic that we did before. So let me replace this to be black. So it's right. Remember, we have liquid and we have gas. And now we have spontaneously flow from phase liquid to gas. Or the way we can say, we define my DnH2O is the number of mole of H2O flow from liquid to gas. And this is always a positive number. Positive non-zero number. Describes how much water is being, what's the number of mole of water liquid that's being transferred into vapor at 5,000 Kelvin, right? And using the same logic, we get that DnH2O equals to negative of DnH2O liquid equals to DnH2O gas. Right, so that's the same logic we used before. And plug in our original expression here. We get it to be mu H2OL, the chemical potential of liquid water, times negative of my DnH2O plus chemical potential of my gas phase water times DnH2O smaller than 0. Or simplify the term, we take DnH2O out, we get the mu H2O minus mu liquid H2O to be smaller than 0. Or the other way to put it is this one is smaller than 0, so my mu H2O liquid must be larger than my mu H2O gas. All right. So if we generalize our conclusion here, what we're getting is, let's say, any substance J. Now in here, our substance J, let me just make some space. Right, any substance J. So my substance J is water, flows spontaneously from a phase with higher chemical potential. So in here, the phase with higher chemical potential is my liquid, to a phase with lower chemical potential. All right, let's read it again. What did we derive? Is we used this expression and used the nature of knowing that dg is smaller than 0 prior to equilibrium. We find out that this summation of my double summation must be smaller than 0. And by expressing the number of H2O in liquid and gas phase, we find our relationship here. And what we derived at the end is the chemical potential of my liquid water must be larger than the chemical potential of my gas water for a irreversible vaporization of my water. Right? Or the other way to put it, we generalize our conclusion to say that substance J flows spontaneously from a phase with higher chemical potential to a phase with lower chemical potential. All right. And to take one more step further, trying to give chemical potential a more easy to understand physical meaning, let's compare our chemical potential with temperature. So it works similarly to temperature and heat flow. So imagine we have two objects of different temperature. One is hotter, one is colder. Right, so because of the temperature differences, there will be spontaneous heat transfer from the hot object to a cold object. And the direction of that heat transfer is governed by an intensive property, which is temperature. All right, so the temperature is an intensive property that governs the direction of heat transfer between a higher temperature object to a lower temperature object. Now, likewise, we now define our chemical potential. So chemical potential tells us the direction of a flow of a substance J from phase beta to substrate J in phase delta. Right, so depending on the chemical potential of the substance in specific phase, it tells us the direction or in which direction the phase transfer will take place. So the phase transfer always takes place, or we always have flow of my substance J from a phase with higher chemical potential to a phase with lower chemical potential. And the direction of that material flow is governed by an intensive property, which is chemical potential. All right, so this lecture will be a little bit abstract, but effectively what we're using is only like very simple calculus, and I want to end up here to give you an idea about what is chemical potential. Right, so it basically works a similar way as temperature. It tells us in which direction the material transfer will take place, or more specifically this one, we're talking about phase equilibrium. In which direction the phase equilibrium will take place. All right, that's all I have. That's how much I went over in my 9 a.m. section. So I have 2 minutes if you have any questions. If not, I'll also be around for office hour tomorrow. Yes?
Will liquids always have a higher chemical potential than gases?
What? Sorry, can you repeat the question?
Yeah, will liquids always have a higher chemical potential than gases?
Not necessarily. So in this case, remember, we're talking about irreversible phase change at 5,000 Kelvin. But the temperature now, if I drop that temperature into, say, 50 degrees Celsius, then we might have a reversed, different sign of the chemical potential, or different size of the chemical potential, right? So like say, now instead of 5,000 Kelvin, I now have, say, 4 degrees Celsius, right? So my water vapor will more likely to condense into liquid water. Then which one of them have higher chemical potential? Right, so my gas will have higher chemical potential to facilitate the condensation. So the chemical potential itself, it's not a constant, it's an ever-changing term. But by calculating the chemical potential gives us a way to predict how phase transfer will take place. All right, so in our next lecture, we'll talk about reaction equilibrium, and hopefully we'll also do some example problems together on chapter 4. If not, we'll do that practice problem in chapter 4 in our buffer lecture. So that's all from me today. I will see you on Wednesday.